The next section has more to do with how we can apply the information in this unit to a chemical reaction. Now we will look at the reverse process of solubility and determine what concentrations of ions will actually form a precipitate. We will calculate Q just as we did in Unit 11. Q is considered the ion product, though, in solubility equations. But it still represents the same thing. Q is our current snapshot of a reaction in terms of the law of mass action. KSP is our solubility product and our saturation point. If Q is greater than K, precipitation occurs and will continue to occur until the reaction reaches equilibrium. If Q is less than K, no precipitation occurs. So let's apply the idea of Q to a solubility problem. Example problem number 5 is on page 753 in your book. A solution is prepared by adding 750 milliliters of 4 times 10 to the negative third molar cerium nitrate to 300 milliliters of 2 times 10 to the negative second molar potassium iodate. Will cerium iodate, with a KSP of 1.9 times 10 to the negative 10th, precipitate from this solution? As usual, start with writing the reaction and the equilibrium expression. Note the coefficient on the iodate and the exponents on the expression. First thing, we need to determine Q to see if a precipitate even forms. To do this, we need to determine the concentration of the individual ions. We find the concentration of the ions from the initial mixing of the solutions. We will not calculate nitrate or potassium because these two ions are not reacting. We will only focus on the cerium and the iodate ions. Moles of each ion need to be found and then divide by the total volume of the two solutions. Since we are combining these two solutions, we must combine the volume for the molarity calculations. So cerium equals the moles over liters. The moles are 750 milliliters times 4 times 10 to the negative third molarity equals 0.003 moles. The liters combine to make a total of 1.05. Divide the two, and the molarity of cerium is 2.86 times 10 to the negative third. Now we calculate the iodate ion. Again, we take moles over liters. You take the milliliters in liters times the molarity, 2 times 10 to the negative second molar, and you have 0.006 moles. Once you divide the two, the concentrate of iodate is 5.71 times 10 to the negative third. Once we have the current ion concentrations, we put them back into our law of mass action expression to determine Q, the ion product. Note that the iodate concentration is to the third power. So Q equals 5.32 times 10 to the negative 10th. K is equal to 1.9 times 10 to the negative 10th. So Q is greater than K. A precipitate forms. So these concepts about precipitation can also include problems where the concentration of the ions are determined after a solid forms. This is where some of the calculations can get a little more complicated, but I wouldn't call them difficult. After a solid forms, excess ions affect the equilibrium position. These problems include stoichiometry and the ice table. Example problem number 6 is on page 754. A solution is prepared by mixing 150 milliliters of 1 times 10 to the negative second molar magnesium nitrate and 250 milliliters of 1 times 10 to the negative first molar sodium fluoride. Calculate the concentration of magnesium 2+ ions and fluoride minus ions at equilibrium with solid magnesium fluoride. We will approach this problem a lot like we did the last one. We will first determine Q, the ion product, and then determine if a precipitate forms. Write the reaction and the expression. Because magnesium and fluoride are the two ions involved in the solid, we will focus on them. The sodium and the nitrate ions do not participate in the reaction. Moles for both ions need to be found and then divided by the total volume. Refer to example problem number 5 if this seems unfamiliar. We find the magnesium ion concentration to be 3.75 times 10 to the negative third molar. The fluoride ion is 6.25 times 10 to the negative second molar. We put these concentrations into the Q expression and find that Q equals 1.46 times 10 to the negative fifth. Since KSP equals 6.4 times 10 to the negative ninth, Q is greater than K and a precipitate forms. Here is where the stoichiometry comes in. We look to see what ion is limiting and which ion will be in excess. The excess ion will shift our equilibrium, so it is important to see how much of it is left over. We have 0.00150 moles of magnesium ion and 0.025 moles of fluoride ion. They react in a 1:2 ratio, but magnesium is clearly still limiting. All of the magnesium ion will react, and for every mole of the magnesium that reacts, we will need twice as much of the fluoride ion. We use 0.0015 moles of magnesium and 2 times that for the fluoride. So we use 0.003 moles of fluoride in the reaction. Since we started with 0.025 moles of fluoride and used 0.003 moles, we have 0.022 moles left. These are the quantities we have after stoichiometry, and they will be the initial concentrations for our equilibrium. The excess fluoride ions will affect our equilibrium calculations. So the next step is an ice table. Our ice table starts with 0 moles of magnesium ions and 0.022 moles of fluoride ions. With our ice table, however, we need to convert back to molarity for the equilibrium calculations. 0.022 moles of fluoride in 400 milliliters is 0.055 molar. As our equilibrium is established, magnesium gains X and fluoride gains 2X according to our coefficients in our original reaction. We now use our equilibrium values and put them back into the equilibrium expression. X is found to be 2.1 times 10 to the negative 6 molar. This is the solubility of magnesium fluoride in this solution. But we need to apply X to calculate the equilibrium concentrations of the ions. Magnesium is X, so therefore 2.1 times 10 to the negative 6 molar. And fluoride is 2X plus 0.055, the initial concentration. The final concentration of fluoride is 5.5 times 10 to the negative second molar. And this concludes the second video in this series.